Okay, let's give you guys some practice now. So given this function, given this function, find the lowest value of this function for this given constraint. So this constraint here is a straight line, intercept of 2, gradient of negative a half. So this is our constraint. You have to remember the constraint lives in the 2D plane, in the x, y plane. You have to, no matter what, be living on this straight line. And then this surface is this. So to have an understanding of this surface, complete the square on this. So that would be x minus 1 squared minus 1, and then looking at this, complete the square on this, y minus 1 squared minus 1. So really that becomes x minus 1 squared plus y minus 1 squared, and then minus 2. So minus 2. So you can tell that this thing here is really a paraboloid that has been moved across by 1 in the x direction and moved across by 1 in the y direction, and the lowest point will be at negative 2. So you can build up a rough understanding in your mind. Well, anyway, that will then give you this surface here. Find the lowest value of this for this given constraint. So press pause and have a go. Okay, so to do this, let's plot. Let's plot the level curves for this function. So when you jump to Desmos, when you jump to Desmos, punch all these in. So this has an elevation of 0. So that's your 0 here. This has an elevation of 1. This has an elevation of negative 1 and an elevation of 2. And this is your constraint. So so jumping back to here, so your job is to find the lowest value of this function. You see, along here there are millions of these level curves, and and the lowest point will be when the gradient vector. So if you work out the gradient vector of this blue line, it will be all along here like this. Well, the lowest point will be when, the lowest point will be when the gradient vector of this, of the blue line, is in the same, it differs from the gradient vector of the circle. Maybe it's in this direction, or maybe it's in the same direction, but the gradient vector of the circle must be equal to some scalar constant with the gradient vector of the blue line. So this is what we're doing here. We've got to turn this into, we've got to turn this into a function. At the moment it's of this form here. At the moment this is of this form. We want to turn it into a function of this form, and then it spits out an elevation. So so let's turn this into that function, which is this thing here, and this was our original function here, so that we can compute the gradient vector of this and the gradient vector of this. And I've already explained why in the previous video. So so turn this into this function here, and then compute the gradient vector of both. So the gradient vector of both will be, so take the partial derivative with respect to x first. So that would be this. Well, the gradient vector of this will be given by this. Gradient vector of this will be given by this. We want to find x, y, and lambda in such a way that this thing equals this thing here. So now we can put this into here. That will then give us this thing here, and then put this thing into here, and then you've got your lambda here, and the lambda. Well, put this into here, it will then give you this. So so that will then take us to here. So when you get to this stage, you're really looking for lambda. You're really looking for x, y, and lambda in such a way that this thing here will be the same as this thing here. Well, let's simplify this. That's the same as us saying that this thing must be the same as this thing. So if you look at the I component must be the same. So that would imply that this is true. And then looking at the j component, that's the same as you demanding that this thing is the same as this thing, which is this thing here. So you trying to satisfy this is the same as you trying to satisfy these two conditions. So remember, we are trying to find x, y, and lambda in such a way that these two will be true. So do whichever method you want, but just eliminate something when you get to this stage here. It turns out that it's quite easy to eliminate lambda. So let's times everything here by 2. So that will then give us this. So looking at this and this, we're trying to eliminate lambda here. So let's get this equation, take away this equation. That will then give us this, and then tidy this up. Well, y will be this. So so hang on. So you trying to satisfy these two conditions is the same as you trying to find a value of y and a value of x, where this side equals this side. Well, if you punch this into Desmos, it will then give you this. Hang on. Punch into Desmos, it will then give you this. Hang on. It will then give you this line, this black line here. So you staying on that black line will automatically satisfy these two conditions. But really, we want this particular point here, because no matter what happens, you have to stay on that blue line, and really we are searching for the intersection of the two. And let me go back a few steps. Hang on. Let me go back a few steps to illustrate something to you. When we computed the gradient vector of this and the gradient vector of this, I forgot to illustrate this to you. If you compute the gradient vector of the circles, it will then give you this. So let me illustrate this. Hang on. Bear with me. A and B, and let me just turn this on. There. So this thing here, you can see is a gradient vector, represents a gradient vector of all the level curves. So so if you jump to this elevation here, it represents the gradient vector. So let me jump up another level here, and so on. So now if you look at the gradient vector, hang on, let's look at the gradient vector for the blue line. So the gradient vector of the blue line, let me turn this on, and hang on, for the blue line, there. For the blue line, the gradient vector will always be the same. There, that's the gradient vector. So you see at this point here, you can see that don't forget there are lots of other smaller circles in between as well. And then we are looking for the intersection of the two, because at the intersection of the two, the gradient vectors for the two functions would differ by some sort of scalar constant. So in short, we are looking at the intersection of those two lines. So going back to here, we were here. This thing here represents the black line. Represents this black line here. Where is it? It represents this black line here. So hang on. So going back to here. So looking at the black line here, we can now put it back into the original constraint. So this was our constraint here. So we can put this into the y here. That will then give us this thing here. So blah 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 x would be this, and once you know x, you can work out y. Y would be this, because once you know x, once you know x, you can put it back into here, and that will then give us this thing here, y. So now we know x and y. Now we know x and y. So now we know the intersection occurs. This is our x and this is our y. And then if you want to know the elevation, put x and y into the original function, into the original function, into the original function. This was our original function, and then that will then give us the elevation. So so the elevation will be this, and the lowest value will occur when x equals this and y equals this. Okay.